DC series circuits. We'll cover voltage, current, resistance and power consumption, as well as using a multimeter and a chance for you to test your knowledge at the end. When we connect components in an electrical circuit, we can connect them either in series or parallel, or we can combine these to make a series parallel circuit. We're going to start with the series type, which is the most basic, but we'll cover the other types in other tutorials. Do check those out, links down below. So if we place two components in a line end to end, or with some wires in between, then these are connected in series. The electrons only have one path they can take, so they will all flow through each of the components. By the way, in these animations, I use electron flow, which is from negative to positive. You might be used to seeing conventional current, which is from positive to negative. Electron flow is what's actually occurring. Conventional was the original theory, but it's still taught because it's easy to understand. Just be aware of the two and which one we're using. Resistance in series circuits. Each component will have a certain resistance. The resistance opposes the voltage being applied. We measure resistance in a unit of ohms. In series circuits, we find the total resistance for the circuit by simply adding together all the resistances. We label each resistor with a capital R and number them R1, R2, R3, etc. The total resistance is shown with a capital letter R and a subscript T, which represents the resistance total or the total resistance. To calculate the total resistance of a series circuit is super easy. We simply add together the resistance value of each resistor. Let's say we have a circuit with a single resistor. That's our R1, and this has a value of 10 ohms. So what is our total resistance? Well, that's easy. The total resistance is just 10 ohms. If we then added a second resistor, R2, with 5 ohms of resistance into the circuit, the total resistance is now 15 ohms. That's because 10 ohms plus 5 ohms. If we added another 5 ohm resistor, then the total resistance is now 20 ohms. In reality, the wires too will add some resistance, but this is very small. You might need to account for this depending on how accurate your design needs to be. Current in series. Current is the flow of electrons. It's like water which flows through a pipe. The higher the current, the more electrons are flowing. We measure current in the unit of amperes, but engineers tend to shorten this to just amps. Now we have covered current in detail in our previous video, do check that out, links down below. We measure current by placing an ammeter into the circuit for the electrons to flow through. This is like a water meter in the sense that water must pass through it for us to measure it. We can connect a multimeter into the circuit to also read the current. The multimeter must be placed into the circuit for us to take a reading, because the current will flow through this. The meter will add some resistance to the circuit, but it's such a small amount that we can usually just ignore this. If you don't have a multimeter yet, then I highly recommend you get one. They are essential for troubleshooting and also building your understanding. I'll leave some links down below for which one to get and from where. We can calculate the total current of the circuit by dividing the voltage by the resistance. So if we connect a 10 ohm resistor to a 9 volt battery, 9 volts divided by 10 ohms gives us 0.9 amps. If we added another 5 ohm resistor to the circuit, that gives us 15 ohms of resistance. So 9 volts divided by 15 ohms equals 0.6 amps. And if we added another 5 ohm resistor, that gives us 20 ohms of resistance. So 9 volts divided by 20 ohms equals 0.45 amps. So we can see that as we add more resistance to the circuit, the current reduces, so less electrons are flowing, and that means we can do less work. We can visualize that by connecting an LED with a resistor into a circuit. The higher the resistance, the dimmer the LED will be. We can also use resistors to protect components in the circuit. If I use a 100 ohm resistor with a 9 volt battery, the current will be around 0.09 amps or 90 milliamps, and that will be too much and it will blow the LED. If I use a 450 ohm resistor, the current will be around 0.02 amps or 20 milliamps. So the LED should be okay. If I use a 900 ohm resistor, the current will be 0.01 amp or 10 milliamp, and the LED will be very dim then. In a series circuit, the current is the same throughout the entire circuit. That's very important, so do remember that. If we place the meter here or here, we will get the same reading. That's because there is only one path for the electrons to flow and they will all move together in the same direction, so the current must be the same. It doesn't matter where we measure or where we place the resistor, even if we swap the order of the resistors. The current will be the same anywhere in a series circuit. Voltage in series. Remember, voltage is the pushing force of electrons. It's like pressure in a pipe. The higher the pressure, the more water can flow. The higher the voltage, the more electrons can flow. We can see that by varying the voltage to a lamp as illustrated here. The lamp increases in brightness as the voltage increases. When we measure voltage, we're measuring the difference or potential difference between 2 points. If we read across a 1.5 volt battery, we get a reading of 1.5 volts. But if we try to measure the same side, we wouldn't read any voltage. We can only measure the difference between 2 points. If we place a 9 volt battery into the circuit, we apply 9 volts to the circuit. We can increase this by wiring the batteries in series. So if we place 2 9 volt batteries in a circuit in series, then we get 18 volts. 3 9 volt batteries will give us 27 volts. Let's take a 9 volt battery and add an R1 resistor of 10 ohms to the circuit. If we use a multimeter to measure across the resistor, we get a voltage reading of 9 volts. If we add another 10 ohm resistor, we get a reading of 9 volts across the 2 resistors, but we get a reading of 4.5 volts if we measure across either of the resistors individually. So the resistors are dividing the voltage. If we replace the R2 resistor with a 5 ohm resistor, the total voltage would again be 9 volts, and that's what we see if we measure across the 2 resistors. But if we measure across the 10 ohm resistor, we see a voltage of 6 volts, and if we measure across the 5 ohm resistor, we see 3 volts. We'll look at why that is just shortly. If we added another resistor, R3, with 5 ohms into the circuit, we again get a total voltage drop of 9 volts across the 3 resistors. Across the R1 10 ohm resistor, we read 4.5 volts. Across the R2 5 ohm resistor, we read 2.25 volts. And across the last R3 5 ohm resistor, we again see 2.25 volts. We can combine these readings to find the voltage at different parts of the circuit. For example, if we measure from the battery across R1, we see 4.5 volts. If we measure from the battery across R1 and R2, we get 6.75 volts, because 4.5 plus 2.25 volts. So unlike current, where it's the same throughout the circuit, the voltage will be different throughout a series circuit. This shows us that the voltage is reduced by each resistor, so the resistor creates a voltage drop. That's the purpose of the resistor, to reduce the voltage or the pressure. What's happening is the resistor creates a more difficult path for the electrons to flow through, and as they flow through, they will collide with other electrons. This collision will convert the energy into heat. The same amount of electrons will enter and exit the resistor. They will just have less energy or pressure as there's been a voltage drop. We can calculate the voltage drop across each resistor individually by multiplying the total current in the circuit by the resistance of each component. Remember, in a series circuit, the current is the same anywhere in the circuit. The total voltage drop will be the total of all the individual voltage drops combined. The first circuit, there was a 10 ohm resistor by itself. The circuit had a current of 0.9 amps, so 0.9 amps multiplied by 10 ohms equals 9 volts. The voltage drop across the resistor is therefore 9 volts, and that's the same as the voltage source. The second circuit had a 10 ohm and a 5 ohm resistor together. So the first resistor voltage drop is 0.6 amps multiplied by 10 ohms, which gives us 6 volts. The second resistor was 5 ohms and the current was the same, so 0.6 amps multiplied by 5 ohms equals 3 volts. The total voltage drop is therefore 6 volts plus 3 volts, which gives us our 9 volts. The third circuit has a 10 ohm and 2 5 ohm resistors. The circuit had a current of 0.45 amps. So R1 is 0.45 amps multiplied by 10 ohms, which gives us 4.5 volts. R2 and R3 will be 0.45 amps multiplied by 5 ohms, which gives us 2.25 volts on each. The total voltage drop is therefore 9 volts, which is 4.5 plus 2.25 plus 2.25. Power consumption in series circuits. How do we measure power consumption of the circuit? Well, we can use the following equations. We can either use power, which is watts, equals voltage squared divided by resistance, or we can use power equals voltage multiplied by current. You might be wondering, how can a resistor consume power? Well, as the resistor is creating a voltage drop, the electrons are losing some energy. Where is this energy going? Well, the electrical energy is being converted into heat. And if we look at some resistors under a thermal imaging camera, we can see the heat is being generated. So the power consumption is actually the heat being dissipated from the circuit. So in this circuit, the resistance is 10 ohms, the battery is providing 9 volts, the current is 0.9 amps, and the circuit consumes 8.1 watts of power. How do we calculate that? Using method 1, 9 volts squared or 9 multiplied by 9 is 81, divided by 10 ohms is 8.1 watts. Alternatively, 9 volts multiplied by 0.9 amps equals 8.1 watts. In the circuit with the 10 ohm and the 5 ohm resistor, the total resistance was 15 ohms, and the current was 0.6 amps. So 9 volts squared is 81, divided by 15 ohms is 5.4 watts. Or 9 volts multiplied by 0.6 amps equals 5.4 watts. In the circuit with the 10 ohm and the two 5 ohm resistors, the total circuit resistance was 20 ohms, and the current was 0.45 amps. So 9 volts squared is 81, divided by 20 ohms gives us 4.05 watts. Or alternatively, we can use 9 volts multiplied by 0.45 amps, which equals 4.05 watts. Okay, so now it's time for you to test your knowledge. So this LED can't exceed a maximum current of 0.02 amps or 20 milliamps, otherwise it will burn out. So if we connected it to these resistors and a 9 volt battery, what will the approximate current in the circuit be? I'll leave a link in the video description down below for the answer. Okay guys, that's it for this video, but to continue your learning, then check out one of the videos on screen now and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, Instagram, LinkedIn and theengineeringmindset.com.